Hello, welcome to another module of this course, Analog Circuits. In the last module we covered only the introduction, where we introduced you to why analog circuits are important. In this module we are actually going to start with the details of the course. First topic in this course is about poles and zeros. So what happens is that poles and zeros are related to the concept of transfer function of a system. Now, transfer function is a frequency domain technique for finding out the solutions to the, or rather finding out what the output of a system will be to various inputs. Transfer function is only applicable for linear systems. So let us first let us start with the what is a transfer function. So transfer function can be defined as a rational function in the complex variable S. Where S is given as sigma plus j omega. So this is the complex variable S. This is the real part. This part is the imaginary part. We know what is a transfer function, but what is its advantage? The first thing is this variable S, this is a frequency domain variable. Okay. So this entire transfer function, suppose as I said, if Ts represents the transfer function of a linear system, and I mentioned that Ts transfer function is a rational function. So I might be able to write it like this. Okay. So a rational function is basically a function which involves a numerator and a denominator. An alternative way of writing this transfer function could be, so we have a numerator function and a denominator function, and instead of writing it like a polynomial, we can write it in a factorial form. So then we will have S minus Z1, S minus Z2, S minus Zm minus 1, S minus Zm upon S minus P1, S minus P2, S minus and so on till S minus Pn minus 1, S minus Pn. So you see here we have written the same transfer function in a factorial form. So this S minus Z1, S minus Z2 and so on, these are the factors of the numerator, and S minus P1, S minus P2, these are the factors of the denominator. Now this Ns is the numerator polynomial, ds is the denominator polynomial. Now, before going into the definition of what is the poles and zeros, I would like to point out something, that we are operating in the frequency domain. As I said, this S is a frequency domain variable. Usually this transfer function is found out, we can, this numerator represents the output and the denominator represents the input. And the way to find out the input and this ns and ds is often by first finding out the Laplace transform of the output and then dividing that by the Laplace transform of the input. Okay. So, that is how it is done. That is how we find out the transfer function of a linear system. So, as I said, before going on to the formal definition of the poles and zeros, let us discuss the advantages of operating in the frequency domain. So, first is, once you are in the frequency domain, very high order systems can be analyzed easily. So, now what do you mean by high order system? High order system, basically the order of a system is that degree of differentiation. For example, say if your V out is VO represents the output of a system, and say the input, the output is related to the input like this, where Vi is the input, so here in this case the order of the system will be 3. This is a linear system, by the way, and since the highest derivative order is 3, the order is also 3. So, the order of a system is the highest order of the derivative that relates the output to the input. So, in the time domain, as you can see, if we had tried to analyze the system in the time domain, we would have to find out the solution of this complex differential equation, whereas in the frequency domain, this entire input and output relationship is reduced to a simple polynomial. For example, this becomes equal to this, sorry, here this will be K3 Vi, just note this change, plus K3 Vi of S. So, you see this entire input and output relationship, once we take the Laplace transform on the left hand side and the right hand side, and we go to the S domain, which is the frequency domain, we see that this input and output relationships are now described by means of a polynomial. So, the analysis of a polynomial is much easier than the analysis of a derivative terms. Okay. So, a differential equation gets transformed to a simple linear equation. So, this is the one advantage of working in the S domain or the frequency domain, which is that very high order systems can be simplified and analyzed easily. What is the other advantage? Now, when we will see later on that when we try to analyze the stability of a system, stability analysis we will see is much easily done in frequency domain as compared to time domain. One reason is because in the time domain, to understand the stability of a system, we have to let the system run for a long time. So, if we a system, whether a system is stable or not, it will ultimately be reflected in the time. That is, if the output collapses or becomes null, or if the output becomes too high, then we say the system is unstable. But then to actually see in time domain whether a system is stable or not, we have to go on analyzing the system over a very long time. Perhaps maybe the system becomes unstable after a very long time. Some systems may become unstable after a very short time, whereas there are systems which may become unstable after a very long time, and initially it may not be obvious that the system is actually unstable. A frequency domain analysis, on the other hand, considers the overall response of the system in the frequency domain, and therefore we do not have to wait or analyze the system over every time instance till it becomes unstable. A frequency domain analysis is therefore much easily gives a more comprehensive view of the stability of a system, and that is why working with transfer functions we will see that it is much easier to find out the stability of a system. Now, coming back to that equation for the transfer function which I mentioned earlier. So, we see that our numerator and denominator can be factorized, the ns and ds, which represent the numerator and denominator polynomials. They can be factored like this: ns is factored as s minus z1, s minus z2, and so on. ds is factored as s minus p1, s minus p2, s minus p minus pn minus 1, and so on. Now, if you consider the denominator polynomial, which is now in a factorized form, if s is equal to any one of these p1, p2 or pn, then we see that the output will blow up. If we had an input, and if we put s equal to, if we had an input to the system, and if we make s equal to any one of these values, the output will simply blow up, because the transfer function itself becomes very high or infinite for s equal to p1, p2, and so on. So, these points where s equal to p1, p2, p3, and so on till say pn, these points p1, p2, p3 are called the poles of the system. So, I can say that, let me write it down here, it will become clear. P1, P2 till Pn minus 1, Pn poles, Z1, Z2, Zm minus 1, Zm represent the zeros. They are called zeros because if we make s equal to any one of Z1, Z2 till Zm, any one of them, we will find that the output collapses or becomes 0. Therefore, they are called as zeros. Okay. Now, all these values, this P1 and P2 till Pn or Z1, Z2 till Zm. So, these are the roots of ns, and these are the roots of ds. Since the coefficients of ns and ds are real, all p's and z's, pi's and zi's should be purely real or in complex conjugate pairs. Okay. So, we should have say p I is equal to x plus j plus minus jy, or p I should be simply equal to x. Okay. So, either Pi's and Zi's should be purely real, or they should be in complex conjugate pairs. So, let us consider an example. Suppose we have a linear system whose input and output are described by this differential equation. Now, taking Laplace transform on both sides, we get y of s multiplied by s square plus 5 s plus 6 is equal to 2 u of s plus 1. Okay, let me, there is a slight correction, it is du plus ut. So, then we have u of s here. Just note this correction, this is, okay, let me write it down at the bottom, this is u of t. So, then after taking Laplace transform on both sides, we have this equation. So, now the transfer function h s, which is equal to y of s upon u of s, will be equal to 2 s plus 1 upon s square plus 5 s plus 6. So, what are the factors in the numerator? The factors are 2 s plus 1, which is a single factor. What are the factors in the denominator? So, this transfer function I can rewrite it as so the 0, the single 0 is at minus half, and the poles are at minus 3 and minus 2. Okay. Now, one thing you must note, that the order, suppose m is the order of ns, that is the numerator polynomial, and if n is the order of the denominator polynomial ds, then for physical systems you will always find that m is lesser than n. And the reason it is so is because we see that had m been allowed to be higher for n, then what would happen is that when s tends to infinity, that is when the frequency is very high, the output, say y of s, also tends to infinity, which is not observed in physical systems. In physical systems, it is always observed that as the frequency goes on increasing, the output of any system will tend to decline or remain the same. It will not exceed the value, and therefore, for physical system, that is why this limitation for this physical systems. Now, any based on this transfer function, we see that every linear system has a number of poles in it. So, if we can then write the output of any system in this form, okay. This follows because we know that h of s is given by ns upon the denominator polynomial, which say the constant s minus p1, s minus p2 till s minus pn. Now, it is possible to factor this h of s like this, it is possible to obtain the partial factors of this h of s and write this whole transfer function in this form. Now, any output y s will be given by h of s times the input x of s. So, then we see that after this equation we will have the y s like this, k 1 x of s upon s minus p 1 plus k 2 x of s upon s minus p 2 until k 3 x of s s minus p n. Okay. So, then you see that if we try to find out the time domain solution of this equation, how will it be? The time domain solution of this equation will indeed be what I wrote it like this, where lambda I represents the various poles of the system. So, here we are using this lambda I interchangeably with this p i's. Okay. So, if we find out the time domain or the inverse Laplace transform of this right hand side of the equation, then it will look something like this. So, in other words, the poles of a system completely determine the response. Okay. They are more important than the numerator, as you can see, because the output will be dependent on what the values of the poles are. Now, the denominator polynomial is the source of the poles, right. So, that is why, and since the poles play an important role in determining the overall response of the system, therefore, this denominator polynomial is also sometimes known as the characteristic equation. And the roots of the denominator polynomial, which are also known as the poles, are also known as eigenvalues. So, eigenvalues are the same as the poles of a system, except that eigenvalues are a term used for characteristic equation, whereas poles are a term used for the transfer function. So, depending on what the values of the poles are, you will get various kinds of responses. For example, if we plot on the complex S plane, suppose our complex S plane is like this. Okay. The poles can be in either in one of these regions only, and since we said that the poles will always be in conjugate pairs, so these two are conjugate pairs, these two are conjugate pairs. If suppose the poles are on the x axis, that is on the sigma axis, but on the right hand side of the S plane, then the output will be something like this. So, this is a case of exponentially increasing. And therefore, does not represent a stable system. This is the case of an unstable system. Similarly, here also these two, if we see, here the output response will be of this nature, A plus sigma t multiplied by sine of omega t plus phi. This is also exponentially increasing, except that in this case the exponentially increasing function is a sinusoid, whereas here it is straight away exponentially, it was straight away exponentially increasing. So, So, here also since the output goes on expanding unchecked, these two, all these three represent unstable. Okay. So, I will just write unstable, this is unstable, this is also unstable. What about the case when the poles are on the y axis? So, when they are on the y axis, the output will be something like this. This is, yeah, this is plus only, not minus. So, here when the poles are on the y axis, the output will be C e raised to plus minus j omega. So, here it is minus, plus and minus both. So, this represents what we called as oscillatory system. What it means is that here the output neither increases nor decreases, but simply keeps oscillating. The amplitude remains the same, but the amplitude does not decrease or increase with time. For this particular case, the amplitude goes on increasing with time. What about these two cases? Now, in these two cases also we see that, let us see what kind of, suppose your poles are at these two positions, then your output will be of this nature. Now, this represents a sinusoid whose amplitude progressively goes on decreasing with time. Okay. Here the amplitude will go on decreasing with time. So, this is what we call a decaying sinusoid. And therefore, represents a stable system. This output for a bounded input, we will get an output which will gradually decrease with time. This is what we want. In this case, when you have any input which may be bounded or unbounded, if you have a unbounded, then anyway the system will be, the output of the system will go on increasing. But even if we have a bounded input, that is an input which after some time decreases or becomes 0, even then for this particular system we will have the output which goes on increasing with time. For these two cases also, for a bounded input, that is an input which becomes 0 after some time, the output will keep on oscillating, and therefore is not a stable system. And finally, for this particular case, we will get an output which is of this nature. So, this is exponentially decaying. This also, as we can see, for a bounded input, since the output becomes 0 after some time, therefore, this particular system, a pole placed at this region also represents a stable system. So, with this, we conclude our discussion on poles and zeros. We will take up this part on poles and zeros later on while discussing the stability and frequency response of systems of filters especially. But this is not the actual analog circuit part of the course. This was just an introduction to a tool that we often use while discussing linear systems, and this is a very important tool. This is a frequency domain tool, and as I said, it is important because it gives an overall idea of the system without having to analyze the system for every time instance. So, it can, as I mentioned earlier, it can give the response of it can be used to analyze the response of a very high order system, and also the stability, which is an important aspect of any analog circuit. So, in the next module we will start with op amps, which is where we actually get to introduce some of the analog components that are frequently used. Thank you.